All right, let's try a practice problem. I also have to tell you that I misspoke a little bit in the last video. I was just Googling this and checking that what I told you was correct. I called the refrigerant Freon, and it turns out that Freon is actually a registered trademark of many different types of refrigerants. You have to be a little bit more specific. The one that is very bad for the environment and that's starting to be phased out in the United States is R22. And this one is actually, let me look up, it is chlorodifluoromethane. So it is CF2CLH. And it's very bad for the environment. Like I said, any new air conditioner that you get has to be replaced. So mine has R410A refrigerant. And this stuff is a lot better for the environment. The reason why I had to have my air conditioner replaced is because I had my air conditioner serviced, and the technician told me that I had half the amount of R22 refrigerant that I should have had. So option one to fix it would just be to find more R22, which is borderline illegal, and refilling it and potentially doing harm to the environment, because if I have a leak in my system, I would just be leaking this R22 refrigerant into the environment, or I could have replaced my system and put in brand new R410A. I chose to go with the latter because I like to do my part and help the environment whenever I can. Reason why I'm not using R410A for this problem, though, is because it's actually a mixture. So we haven't talked about mixture yet. R22 is a pure component. It's chlorodifluoromethane, like I just mentioned. So let's say that we know that R22 is well modeled by the van der Waals equation of state, and I have van der Waals constants. All I want to do now is calculate the vapor pressure at 15 degrees Fahrenheit. So again, Gibbs phase rule is a good place to start. I have a single component, and when I have vapor pressure, I have phase equilibrium. So I have 2 plus 1 component minus 2 phases is equal to 1 degree of freedom, and that 1 degree of freedom is specified by setting the temperature. Therefore, my pressure, vapor pressure, is also set. So because T is set, is specified, P star must also be specified. Okay, what now? Well, one option would be, if I had a phase diagram, I could simply go to my phase diagram and look up and see where the vapor-liquid equilibrium curve is intersected for 15 Fahrenheit. But remember, in most of these thermodynamic problems, we do not have, or we pretend not to have, access to the thermodynamic data. So we have to find the answer using first principles. In this case, the first principle that I'm going to use is one of my equations for the fugacity. So I'm going to use this equation in order to solve the problem. So I'm just going to copy this down below. All right, so I chose the version with Z to illustrate how you would go about solving this equation. I'm also going to need the van der Waals equation of state. So I know van der Waals is P is equal to RT over V minus B minus A over V squared. I don't have Z in this equation, so what I'm going to do in order to get it in a form of Z is I'm going to multiply the entire equation by something that will make this equal to Z. So Z is PV over RT. So if I multiply this entire equation by V over RT, let's see what we get. So the left-hand side is PV over RT is equal to, now the RTs will cancel, and I'll get V over V minus B is equal to, one of these V's will cancel on the bottom, so A divided by VRT. And this is equal to Z. So this is the van der Waals equation of state in Z form. So in terms of the compressibility. All right, now if I go up to my equation now, I can plug in this expression for Z in order to take the integral of this term. So inside the integral, I've got 1 minus Z over V under bar. So I'm going to say 1 minus Z is 1 minus V divided by V minus B minus A over V RT, all over V is equal to 1 over V minus 1 over V minus B minus A over V squared RT. This is my integrand. This is 1 minus z over v. Okay, so in order to evaluate this integral, I need to integrate this with respect to v. So the first term, 1 over v, if I integrate that, and the limits of integration, which I'll use in a second, are v is equal to infinity to v is equal to v under bar. So the first term is ln of v. Second term is ln of v minus b. And my third term is, I've got a v squared in the bottom. A, R, T are all constant. T is being held constant at 15 Fahrenheit, remember. So I'm going to get a negative from the integral, which is going to cancel with that negative out front. So it's plus A over VRT. Evaluated at V is equal to infinity and V. Now, if I plug in infinity, I'm going to have problems because I've got ln of infinity, which is undefined. However, I'm going to use the property of logarithms and simplify this and say that ln of two things subtracted is just ln of v over v minus b. So I'm putting it both in the same argument of an ln function, plus a over VRT. Now if I plug in infinity, I've got ln of infinity over infinity, which cancels to 1. ln of 1 is 0, plus 1 over, or a constant over infinity, which is also 0. So I don't have to worry about the bottom limit of integration. When I plug in v under bar, I'm just going to be left with this exact function. Now to finish out, so that's the evaluated integral. I'm going to take the rest of the equation. So that's ln of phi is z minus 1 minus ln of z. So I'm going to keep that as well. So ln of phi is z minus 1 minus ln of z, and then minus, plus all this stuff, sorry. Plus that term. I know it should be, is it minus? Let me check, make sure. And sorry about this, I made a mistake. So when I did 1 minus z, I should have said 1 minus, and then since this is z going there, I should have had a plus there, which makes that a plus, and which means that the minus comes out front and the minus stays there. And this should be a minus again. I'm propagating through the air. Okay, that is correct. This is what it should be. All right, so how has this helped? What is my unknown in this equation? Well, I'm going to apply the equilibrium criteria now. At equilibrium, remember the fugacity of the vapor is equal to the fugacity of the liquid. So how does that help? Remember that phi is F divided by P. So I can use this equation, apply it to the vapor and apply it to the liquid, and use the constraint of my equilibrium condition, and that will satisfy the pressure at which my fugacities are equal. So I'm going to go on to Excel in a second here, but I want to do one more thing, which is remind you what the V versus P diagram looks like for the van der Waals equation of state. So this is a cubic equation of state, remember, and we have an isotherm. So we've got T is 15 degrees Fahrenheit, which is constant throughout this process. So if I plot P versus V, I'm going to have something that looks like this. So this is what the actual data would look like. All right, something that looks like that is the actual data. And remember that the cubic equation of state, like the van der Waals equation of state, I'm going to put dots there at the saturation point. The cubic equation of state will trace this data, and then in order to join it in a way that there is no disruption of the function, it must have a minimum and a maximum. All right, so this light blue part is the part that the data fit function has, but is not physically relevant. All right, so now what I'm asking is, what is the vapor pressure at which I have saturation? So I want to find whatever this pressure is, because this pressure is my saturation pressure. So for any given pressure, I'm going to have 3 solutions to the cubic equation of state, always. Sometimes, so if my pressure is up here, my other 2 solutions may be imaginary, and this is the one true solution. If my pressure is down here, I've got 3 solutions, but remember these 2 don't make physical sense, and my one true solution for V under bar is there. So what I want to find is the pressure at which, again, I've got a V underbar for the liquid and a V underbar for the vapor. This is tricky to do from the equation of state because remember, if I don't know where this actual data ends, right, if I only have the light blue curve and it extends all the way, I don't know if my pressure is here. It could be there, right? I don't know exactly where this jump from the liquid to the vapor phase actually occurs. So what I'm going to do is use solver and guess and check for pressures until I find the value of V underbar liquid and V underbar vapor that I can plug into this equation and make my fugacities equal. So I'm going to pause the video and get into Excel. All right, so here we are in Excel. I've got our data for us all ready to go. I've got the van der Waals constants that are given in the problem. The temperature, so 15 degrees plus 460 is the conversion to Rankine. It's actually 459 point something. I just round to 460. And the gas constant in the appropriate units is 10.73. So I'm going to plot the van der Waals equation of state now. So I want, V is going to be on my x-axis, V and P. So I want to plot V from, let's see, B is 1.6 cubic feet per pound mole. I'm going to start at 5, and I'll increase by 5 every time. So what happened there? So equals this plus 5. There we go. All right, drag it down. Not sure how far we're going to have to go out, so I'll go to somewhere for now. And the van der Waals equation of state is P is equal to R times T divided by V underbar minus B $, divided by A divided by V square. Okay. And what did I do now? Oh, didn't $ the T or the R. Got to $ those. Okay. All right, that looks better. Now I'll highlight the data and insert a chart. See what it looks like. Okay, there's my equation of state. Oh, I'm not modeling the liquid phase, it looks like. Oh. Okay, sorry about the pause. I was doing a little bit of troubleshooting and I actually learned something interesting myself. So in order to make sure that you see the appropriate range of your plot, you should really not step too large of step sizes. So 5 cubic feet per pound mole was too big of a step to see what I wanted to see. So I lowered that down to 0.5. And then I had to do some guessing and checking to get an initial value that made sense. So if I change this at all, so if I go down to 2, for instance, it goes up too fast. I don't get a good picture of the plot that I want to. I could leave it like this and now just adjust the axis to go only up to 500. That's probably a better thing to do. So let's leave it at that. Now, as I was saying, I'm really bothered by how bad this plot looks, but again, it's just to get an idea for what the data looks like. This axis is P, this axis is V. For any particular pressure, I will have in general 3 equations. So where is I'm gonna get a line. Okay, so like say I have 190 degrees for 190 for V underbar, for example. For P, I've got 3 solutions for V. Now potentially this could be the saturation pressure, in which case my volume of the liquid would be whatever value for V this is, and my volume for the vapor would be whatever value for V that is. The middle value is always going to be not physically relevant. So the higher value will be my molar volume of the vapor, lower value will be molar volume of the liquid. Although remember, there's only one true value for P because a portion of this plot is not physically relevant. So how do we go about finding what that is? This is where Excel can be useful and powerful again. So I want to set up a solver such that given a value of P, I can calculate what the roots of V are.